Have you ever wondered how power lines interact with each other? We know that electric currents create magnetic fields. When two current-carrying wires are placed side by side, they exert a measurable force on one another through their overlapping magnetic fields. This phenomenon is a fundamental principle of electromagnetism. Depending on the direction of the current flow, these wires will either pull together or push apart. Today, we will explore the physics behind this force and how to calculate it. To understand the force, we first look at the magnetic field created by a single wire. Using the right-hand grip rule, your thumb points with the current, and your fingers curl in the direction of the magnetic field lines. Wire 1 creates a magnetic field, B1, that reaches wire 2. At a distance r, the strength of this field is determined by the permeability of free space, the current, and the distance between the two conductors. Now, wire 2 is a current-carrying conductor sitting in an external magnetic field B1. According to the Lorentz force law, it experiences a force. Using the right-hand rule for force, we find the direction points toward wire 1. Just as wire 1 exerts a force on wire 2 exerts an equal and opposite force on wire 1. This follows Newton's third law. The two wires are attracted to each other because their currents are flowing in the same direction. What happens if the currents flow in opposite directions? If we reverse the current in one wire, the direction of the magnetic force also reverses. In this case, the wires will repel each other, pushing apart with equal magnitude. We quantify this interaction using the force per unit length formula. The force depends directly on the product of the two currents and inversely on the distance between them. The constant μ0 represents the magnetic permeability of a vacuum. Let's calculate the force between two wires 2 cm apart, carrying 5 amps and 10 amps respectively. We plug these values into our formula, ensuring our distance is converted to meters for SI consistency. The resulting force is 5 times 10 to the negative 4th newtons per meter. While this force seems small, in high-voltage industrial applications with thousands of amps, these forces can be strong enough to bend solid metal busbars. Notice the inverse relationship with distance. If we double the distance between the wires, the force is cut in half. Conversely, bringing them closer exponentially increases the mechanical stress on the wire supports. This physical interaction was actually used to define the ampere. 1 ampere was historically defined as the constant current which, if maintained in two straight parallel conductors of infinite length, produces a specific force per meter. Looking from above, when currents flow in the same direction, the magnetic fields between the wires oppose each other, creating a region of lower field density that pulls the wires together. In the repulsive case, the magnetic fields between the wires point in the same direction. To summarize, parallel currents attract, while anti-parallel currents repel. The magnitude of the force is proportional to the product of the currents and inversely proportional to the separation distance. This creates a high-pressure magnetic region that pushes the conductors away from each other. Let's test your understanding. If we double both currents and also double the distance between the wires, how does the force per unit length change? Think about the numerator and denominator in our formula. The force doubles. Doubling both currents increases the numerator by 4, but doubling the distance increases the denominator by 2, resulting in a net factor of 2. Thank you for watching. Generated by Vision Solve AI.